Now let's look at another famous example of one-dimensional Schrödinger equation in bound state. And that is when the potential is a simple harmonic potential. The result is what's called a quantum oscillator. So that's bound state, case A, example number 3, quantum oscillator. That should be interesting. U equals 1 half kx squared. It can also be written as 1 half m omega squared x squared. It's because omega equals the square root of k over m, recall from physics 1b. Okay, so here's an oscillator of mass m oscillating with an angular frequency omega. You put it in a quantum parabolic potential. It's trapped inside. Can you solve for its wave function? Well, this again is a case of symmetrical potential about the origin. Therefore, it is of even parity. The potential is of even parity, and as a result, the wave functions will divide into even and odd cases. It's either even or odd, nothing in between. And the ground state, as you know, is even. The second excited state is even. The fourth excited state is even, and so on. And then also, the first excited state is odd. The third excited state is odd. The fifth one is odd, and so on. So we can utilize that. Also, what about the number of nodes? You do not include positive, negative, infinity. How many nodes do we have for the ground state? 0. Okay, it never touches this x-axis. So that gives us some idea what the ground state should look like. It never touches 0, and it's an even function. So clearly, and also makes sense. That should be, it goes to 0 here and there, and there's no oscillation in the middle. Clearly, it makes sense to put the highest value of psi right in the middle, because being in the ground state doesn't really have much energy. Therefore, it doesn't go very far, right? The most likely spot to find it is in the middle. So you should expect the ground state wave function, even without any series calculation, to look like this. Something like this. Okay, something like this. And we can even roughly figure out how far, what the size of this peak, roughly how wide it is. We can do that a little bit later. So, but that gives us some idea what the ground state looks like. Now, as you increase the energy, it goes from the ground state to the first, to the second, to the third, and so on. The number of the oscillations pick up, and number of nodes also pick up, so it touches the x-axis more rapidly. And what if n goes to infinity? So we're looking at very large n value, so it's a very high energy. As you go to high energy, classical physics should start to take over, right? Because quantum mechanics, when energy is very low, but when n goes to infinity, energy is very high, it should go back to classical physics. Classically, how should you expect a particle trapped inside this potential to behave? Well, it's going to oscillate back and forth between two turning points, right? So, what should the wave function look like? Well, remember, the wave function represents the probability, or I should say more precisely, psi squared is dp over dx. What's dp? The chance of finding this particle between x and x plus dx. Okay? The higher this function, the more likely you can find that particle. Now, classically, this particle goes back and forth, back and forth. Where does it spend more time? It spends more of its time when it slows down, right? And in fact, when it goes through the origin, that's when it's the fastest. So it doesn't spend a lot of time going through the origin, because it travels fast through the origin, and it slows down, slows down, slows down. So by the time it reaches the classical turning point, that is when it slows down to 0. So it actually spends more time near the two turning points and little time at the center. Therefore, the wave function should be higher around these two sides near the classical turning point, and should be lower in the middle with a whole lot of oscillations. Okay, so you can expect when n is very large, the wave function should look very different from this. It should look like this. Here's a turning point. Here's a turning point. It should look like this. Right? There should be a smooth profile. And why does it go higher here and higher there again? That's because when the particle slows down near the two classical turning points, there's more chance of finding them. It spends less time in the middle, so it goes down. And this profile depends on how fast it is. The faster it moves, the lower this profile, and therefore it has to do with the speed. So this is what you expect for large n. And this one expect for n equal to 1, the lowest n. For n equal to 2, the first excited one, it's an odd function, has to go to 0 in the middle, so it should be something like, something like that. Okay, something like that. this gives us an idea what to expect even before we start our calculation. So at this point, let us start to try to solve the Schrödinger's equation for this important special case. We're going to start from the ground state. So here is our solution. Try to find our solution to the ground state. This is the Schrödinger's equation written down for the simple harmonic oscillator. The ground state, according to our general idea, it is of even parity with no nodes. Okay, so it should look like this. How do you find a mathematical expression? Well, if you look at this equation here, it's not something very easy to solve because here you have the x squared. Okay, it's not a constant. You know, solve it. What if it's a constant here? There's no x squared. Then we have a sine cosine solution or exponential solution, right? But there's an x here. That makes your job harder. So we have to, what we do is we use our physical intuition to guess what the answer is, to come up with what's called a trial solution, and then we can see whether the trial solution actually makes sense or not. For the ground state, we know the wave function should look like this. This looks like some sort of exponential decay, right, on either side. So what are the simplest possibilities when it comes to exponentially decaying functions? Well, there are two possibilities here. Here is x and here is x squared. I mean, you can go x to the power of 4, but why would you do that? And there's not a simple. Let's try the simple ones. If they don't work, then I go with higher choices. So here is x to the first power, here is x to the second power. Now with x to the first power, you have to put an absolute value here, because if you don't, then at negative x, it's going to go to positive infinity when x goes to negative infinity, which doesn't make any sense. So that would make a curve, make a psi function look like this. Okay, and you go x squared. That's a bell curve, right? That's a bell curve, so it will look like that. You know, Gaussian distribution type of curve. Which one of these do you think is more reasonable? Well, they don't look that different, except there's one starking contrast. Here, with x, absolute value, you actually have a kink. There's a kink in d phi dx right here. The d phi dx, the first derivative, goes from a positive value to a negative value. But we just learned before that the first derivative of the wave function cannot jump unless you are at a point where u equals infinity, right? Is u equal to infinity at x equal to 0? No, absolutely not. U equals 0. That's the bottom of the potential well. And therefore, this kink shouldn't exist. Therefore, we're going to root this out. Okay, we're going to root this out. And let's try the next simplest case, e to the negative lambda x squared. What is lambda? Don't know. Will this solve our equation? Well, let's try. Okay, let's plug this into here. Well, there's an overall constant, but don't worry about it here. And we cannot find it anyways from this equation because psi, the constant will just drop out. Okay, so pick this choice. A constant e to the negative lambda x squared. I'm hoping to find what lambda is. Okay, now the next step is quite simple. Plug this psi 1, the ground state wave function, into here. So you replace psi 1, psi 1, psi 1. You have to take two derivatives, and here's the answer. You take two derivatives. And here you just copy. Okay, psi 1 equals e to the negative lambda x squared. The next side, you just copy. Now, there is e to the power negative lambda x squared in every term, here, here, and here. So what I'm going to do is I'm going to factor out e to the power lambda x squared and move all the terms to one side. And this is what you come up with. Okay, here we have two constants. Here got two constants times x squared, and outside is e to the power lambda x squared. Now remember, this thing has to equal to 0 for all values of x, running from negative to positive infinity. But you know, that usually is not possible unless this whole thing is 0, because otherwise e to the negative lambda x squared, that thing is not 0, right, in general for x, arbitrary value of x. So this has to go to 0 to preserve the other side. So this whole thing is 0. Now when this whole thing is 0, means this term plus that term is equal to 0, but that term has a variable in it, x. X again can go from negative to positive infinity, but you don't want this to ruin the fact that this is 0, so the only thing you can preserve that 0 for whatever value of x is to make its coefficient 0, right? So this whole term is 0. You just kill this x squared dependency. That leaves the next one with no choice but 0. That is how you preserve this constant, this identity for all values of possible x. So you get 0 here, 0 here. This first one tells you lambda depends, actually this equation tells you what lambda is equal to. You solve for lambda, and lambda you're going to get this. And once you get lambda, you plug that lambda in from this equation here, you get E naught. So we have found this following, and that is our trial solution indeed solves the differential equation, the Schrödinger's equation, provided that lambda equals m omega over 2 h bar, and provided that the energy is equal to 1/2 h bar omega. The ground state energy cannot be just any arbitrary value. It must be equal to 1/2 times h bar times omega. Okay. Now h bar omega is the same as h times f, because h equals h bar times 2 pi, and omega equals f times 2 pi. So that's how it works. So h times f, as you know, it's the energy of a photon, and we have here an oscillator. It doesn't have to be a photon, a general oscillator, but that certainly is something expected. So here is, by plugging lambda here, we got the expression for the ground state wave function. It goes like this. Okay, it goes like this. Now, the ground state is relatively simple. What about higher order terms? Higher order energy levels. That's not so simple, and I do not want you to suffer through the entire derivation because that's too tedious. But what I will do is to show you the key steps so you have a good idea how this is done. So now let's try to find the solution to the equation for the simple harmonic oscillator at higher energy levels, higher energy eigenstates. And here's my proposal. I'm going to write down the solution to higher order eigenstates as a product of this function and another function. This is, as you know, the ground state solution. Okay, it's got no nodes. But the higher order solution would have 1 node, 2 node, 3 node, and so on. So I expect this to be some sort of polynomial, because for nth order polynomial, it goes down to 0 n times, it's got n roots. And let's try to find what this is. Now, if you plug this solution, trial solution, into the original Schrödinger's equation, then you're going to get an equation for h instead of for psi. And let's see if this is better than the original equation. This is what we come up with if you did that. Is this really a bad equation? Well, it's actually somewhat better than before. We have second derivative, first derivative, zeroth derivative. It would be totally easy to solve if it's not for this x here. You have an x here, which means it's not quite a homogeneous equation, unfortunately. But don't worry, we can always solve an arbitrary differential equation. If all else fails, we are going to introduce our last resort, and that is introducing this expression, the infinite series. I don't know what this h is, but I can always expand h in terms of the infinite series. So I have a bunch of terms, a0 plus a1x plus a2x squared plus a3x to the power 3, and so on and so forth. All I have to do is to find a0, a1, a2, and 3, right? And hopefully at the end I can sum it up once I find this infinite series. So plug that in, okay? Plug that in. It's a lot of work, and I don't expect you to really follow all the work if you don't want to. But what I want to show you is what happens if you did that. I want to show you the important physics that follows next. Once you plug into these expressions, you find that to match the two sides, to make it equal to 0, every term, every power of x should go to 0, and that's what you get. You find that c of n, that is the coefficient, I should say a of n. Okay, a of n, a. This a of n, which is the coefficient of the nth power term here, is actually related to the n plus second power term by this. So given a0, you would get what? a2, right? And given a1, you can find a3 and so on. Now, in general, this term, this thing here, can be just any number. It doesn't have to be 0. And if it's not 0, then that tells me that given a certain an, I can always find it's n plus 2. And given an plus 2, I can even find an plus 3 and so on. So all we have to do is give me two neighboring a's, one even, one odd. And from that, I can find all the higher order a's. And that can proceed to infinity. Okay? This n can proceed to infinity, and you will have an infinite series, which will we set out to do, an infinite series. Now, what's wrong with the infinite series? Well, it turns out mathematically you can show that for this particular infinite series satisfying this thing, which is called a recursion relation. Okay, recursion relation. The problem is, you take that infinite series, even after you multiply by this suppressing exponential term, psi still goes to infinity at x equals positive and negative infinity, which means the wave function is physically untrue. The wave function should go to 0 at positive negative infinity, right? Because the particle never has a chance to go all the way out there. Therefore, we have a problem. We found a solution which does not satisfy the boundary condition at positive and negative infinity. So what do we do? Well, there is one way to resolve this issue, and that is, I don't want to go all the way to infinity for this n. I want to kill the series for, up to a certain value n, say n equal to 7, n equal to 8. I'm going to kill it. In other words, after n equal to 7, nothing exists. There is no A8, there's no A9, and there's no A10, and so on. It's all killed. How do you kill that? Very simple. All you have to do is take this equal to 0 for a given n. Okay? So if you take this thing to be 0 for a given n, then there will be no n plus 2, there will be no n plus 4, and so on. None of these would exist because this is already 0. Right? So this guy will be 0, and then the one after that will be 0 too, and so on. So that's how I shorten or truncate, shall we say truncate, the infinite series to a finite order polynomial. And that's what I expect. The polynomial will give you a finite number of nodes. So here, again, the infinite series does not converge for x equal to plus or minus infinity. And what shall we do? We truncate the series. Okay? That is not because we want to do it, it's because we don't have a choice. We cannot let psi to go to infinity at plus or minus infinity. That will be a violation of the boundary condition. To satisfy the boundary condition, we must truncate the series, and the only way to do it mathematically is to set this thing to equal to 0, and that is how you kill the series short. So that's what we do here. We set this thing to 0, okay? And from here, there's an e here, there's an n here, and you just work out everything you find. E must equal to n plus 1/2 times h bar omega, where n is any integer. 0, 1, 2, 3, 4, and so on. Okay, this is not only the derivation of the energy of n's eigenfunction, it also has a very simple ring to it. It's n plus 1/2 h bar omega. So therefore, the energy gap between neighboring energy values is the same. Okay, what is the energy gap when delta n equals 1? That's h bar omega. H bar omega. You have an energy diagram that's evenly spaced. That was not true for the finite square well or even infinite square well. This is finite. This is the gap is not just finite, but the gap is actually the same for every energy level as you go up. Now, we will see. In fact, we're not going to prove it, but I can tell you from this point, that is, this is the only potential. The simple harmonic potential is the only potential that will give you an even spacing in its energy diagram. So if you find the energy levels, draw a plot of all the energy that we call an energy diagram, you find all the energy levels have even spacing. You must be dealing with what? A simple harmonic potential. It goes like x squared. That's the only possibility. And as a bigger question, let's ask again, why is energy quantized? We saw the energy was quantized in our two previous cases because we have to satisfy boundary conditions, right? As you make transition from one region to another region. Here we have a smooth function, u. There is no region. The whole space is only one region. We never went from region 1 to 2 to 3. But there is still a boundary condition. In fact, there are two boundaries, one at negative, the other at positive infinity for x. And in the previous case, the energy was forced to be quantized because we had to satisfy those boundary conditions. This is no exception here in our case. Why is the energy quantized here? It's because, just like we said before, we had to kill the series short, the series short, Why did we have to kill the series short? Because we had to satisfy the boundary condition at positive and negative infinity. We cannot let psi go to infinity at those locations. And that forced us to write this, which gives us the quantization of energy. So once again, one more example that tells us quantization of energy is a derived condition from the fact that you must find the solution to the Schrödinger equation which satisfies the boundary condition. So it is a natural consequence of applying the wave nature to describe a particle. So I have this energy diagram, E naught, E1, E2, E3, and so on from the textbook. And again, the general expression is n plus 1/2 times h bar omega. And here's n equal to 0 for the ground state, n equal to 1, 2, 3, and 4. And again, the gap, delta E, is h bar omega. Even spacing, one more time, even spacing of energy diagram only occurs for a simple harmonic potential. It's very simple and very elegant. But what about the wave function? Well, the wave function, when you satisfy the truncation condition, the wave function is equal to this exponential function times a polynomial, right? This polynomial has a name. We call it emission polynomial. Okay, and the emission polynomial of index n, for the lowest values of n, I have actually some examples here. This is the lowest order, h0, that's when n equals 0, and it's just a constant for the ground state, which means you just multiply this thing with a constant, so that's the ground state, but we already know that, right? Don't we already know that? We already solved the ground state wave function. That is what it looks like. Just multiply a constant. Okay? That is the zeroth order emission polynomial, n equals 0, and the energy is n plus 1/2 h bar omega, n equals 1/2, n equals 0, so you just get 1/2 h bar omega. That's the ground state energy. There's no node, it's even function. Okay, the next one up, that's the first excited state. It turns out h1 equals x. This is an even function. Multiplied by x, you get an odd function. That's precisely what we expect. First excited state should be an odd function with one node in the middle, x equals 0. That's it, no more nodes. The second excited state, h2, is given by this. This is h2. Given h2, you would have, again, an even function because it's x squared. And there are two nodes because you can let, this is, when you solve for this, x equals plus or minus whatever to make this 0. So there are two nodes. And this goes on and on and on. In fact, I have here a plot of some representative n values for the wave function. This in fact is probability density, so I take the wave function and I square it. Okay, so I get probability density, the chance of finding the particle in a certain location. This is n equal to 0. Okay, again, it's most likely to be found in the middle, so it's a bell curve. N equal to 2 is expected to be even or odd. Okay, 0, n equal to, the ground state is even, so n equal to 1 is odd. This one is even, with two nodes. See here, two nodes. Okay, here is n equal to 5, and you got 5 nodes. 1, 2, 3, 4, 5. Okay, here's 2 nodes, 5 nodes. And here is n equal to 20. That is a large n, relatively speaking, and you got 20 nodes. 1, 2, 3, 4, just count. There are 20 of them. And the interesting thing here is that you get this profile. Okay, you see, the chance of finding this particle is pretty high near these 2 points. That is actually the classical turning point, this point and that point. And the profile goes down in the middle because the particle passes through the midpoint pretty fast. And you can imagine, what if n equals not equal to 20 but equal to 2 million? Then you have such a rapid oscillation with 2 million times crossing 0, so that you don't even see these ups and downs anymore. It's just becomes a smooth function, and that smooth function is the highest at the 2 tuning points, lowest in the middle. That actually represents the classical chance of finding this particle at any given location. So you go back to classical physics for large n values. We have applied the uncertainty principle to the energy levels of infinite potential well, at least in ground state. We do the same thing for the simple harmonic oscillator. This, in fact, is problem number 41 in the textbook. This also gives us an interesting way of estimating the ground state energy without going through all this calculation. Okay, E equals 1 half mv squared plus 1 half kx squared, which is this. So I'm going to rewrite it in terms of the px, the x component of momentum, and x itself. You know there's an uncertainty principle in between px and x, right? So we have delta px times delta x of the order of h bar. But for the ground state, there is a lot of uncertainty because it's the most quantum state, the furthest away from classical. So you expect px and delta px to have the same order of magnitude, and x and delta x to have the same order of magnitude. So replace delta px with px, same order of magnitude, replace delta x with x, and you find that px times x is roughly of the order of h bar. I mean, like h bar over 2, I don't really care, it's just estimating, okay? So x is roughly h bar over px, right? You plug that in, okay? You replace x, there is only px left. So this now becomes a function of px only, x is gone from the uncertainty principle. You have px squared in the numerator, you have a px squared in the denominator. Now, what's so special about the ground state? This is where energy is what? The lowest possible value, right? Well, the ground state is special because it's got lowest possible energy. But you know, as px varies, this term goes up, this term goes down. Is it possible for me to optimize the value of px so that E is minimum? Because that's what the ground state wants, right? Minimum possible energy, right? Well, we know how to do that. You know, just take a derivative, E, with respect to px, set it to 0 because we want to minimize the value of the energy because it's a ground state, right? So we did that, set dE over dpx equal to 0. I can actually get the possible get an expression for the optimal value of px, which will give you the ground state energy, the lowest possible energy. Px is roughly equal to square root of mh bar omega if you did that. And you plug the px into both here and there, you'll get the ground state energy. And it turns out you don't quite get the correct value, you get h bar omega. But you know, that's pretty good because the ground state energy actually is 1/2 h bar omega. We're only estimating, you know, we must have missed some sort of 1/2 and whatever. That is to be expected from the estimation of the uncertainty principle. We cannot expect everything to hit right on the target, but at least it is the correct order of magnitude. And one more nifty observation about the ground state of the simple harmonic potential, then that is something even simpler, dimensional analysis. We learned dimensional analysis from the very first lecture in Physics 1A. And does it work here? Actually, for this problem, yes it does. You know, the ground state energy, the ground state wave function looks like this, right? That's at least according to our intuition looks like this. And in fact, this goes like e to the power negative something x squared. But you know, we don't have to know necessarily that it has to be e to the power something x squared. We do know that whatever it is, it's got a hump with a certain, roughly how wide it is, delta x. We can estimate how wide it is. You know, this width must be calculated from the equation itself. And the equation has only 3 parameters in it, h bar, m, and omega. Everything else just, you know, just variables. And therefore, if you did this correct calculation and you find this delta x, however hard it is, once you get it done, you find it must be a function of h bar, m, and omega, right? And the question is, how does one combine these 3 parameters, h bar, m, and omega, so that I get delta x, which has a unit of length, right? Now, this becomes the standard problem with dimensional analysis. If you plug in the units of h bar, m, and omega, you find this is the only combination of h bar, m, and omega that will give you the correct unit of length. And therefore, delta x should roughly be the square root of h bar over m omega. I mean, there's maybe a constant in front of it, but you know, that's only estimation. This is the order of magnitude of delta x. What does that tell us about delta p? Well, delta p by uncertainty principle is h bar over delta x, and the square root of m h bar omega. That's the same as we just got a minute ago with a different method. And then the energy is k plus u. Okay, k and u are roughly equal to each other because it's a simple harmonic oscillator, and so it's p squared over m instead of p squared over 2m when you have 2k here. And this p is you know, m h bar omega squared. Square root n squared. You see, again, you get h bar omega. Okay, so what we did here was we simply use dimensional analysis to estimate the size of this, the extent of this wave function, and we came up with the same estimation of the energy, of the ground state energy of this simple harmonic oscillator with very little calculation. So this shows one more time the power of dimensional analysis.